So for exam 4, one of the things you should expect would be type 1 and type 2 errors. Now on the test, I will give you what a type 1 and a type 2 error is. You just have to make sure that you can put it into words. So here's the definitions of type 1 and type 2 errors. Put that in words that relate to the problem, and I'll give you a statement of a claim. That's going to mean you're going to need to figure out what HO and HA are, and then decide what a type 1 and type 2 errors. Now, the majority of our test is going to be spent on hypothesis testing. So that'd be stuff like in problem number 2. And for like 4 or 5 questions, I'm just going to hit you with a question of, do you recognize what hypothesis test you need? So the first thing you need to decide is this going to be a 1-sample test or a 2-sample test? And then you're going to need to decide, well, which one of these is it? That'll be part of your work. The other part will be to write down HO and HA. Now, I'll give you one heads up. Part of HO and HA, you should be using these symbols, mu, sigma, or P. What you shouldn't be using is X bar, S, or P hat. If you use those, you're going to lose points, because we test claims about population parameters, not sample statistics. We use sample statistics to test these claims, but these are the symbols that should be part of your HO and HA. So let's do a couple examples, at least enough as time allows for. Starting with the first one here. 198 smokers underwent sustained care program. 51 were no longer smoking after 6 weeks. 199 smokers who underwent regular care program. 30 were no longer smoking after 6 months. At the 1% significance level, tested claim that the success rate for smoking cessation is greater with sustained care. First things first, 1 population or 2 populations? 2. All right, clearly 2. And what amongst these am I testing? Proportion, mean independent, or mean matched pairs? Proportion. Good. So we're testing the claim that the success rate for smoking cessation is greater with sustained care. Right there. So I like it if you use things that are reflective of the problem. So this would be the proportion that quit with sustained care is greater than the proportion with regular care. What's that going to be part of? HA. P sub sustained is greater than P sub regular. And that means here, P sub sustained, good, is less than or equal to P sub regular. And our decision here was 2 population proportion, which would be D. So we okay with that one? Well, because you're looking at a success rate, that's the percentage of people who are not smoking. And percentage is equivalent to proportion. Yeah. Thank you. Let's try a different one. Problem number 3. In the data set in the book, you'll find the weights in pounds for a cola, or of cola for a sample of cans of regular Coke and of Diet Coke. Use a 1% significance level to test the claim that the average weight is the same for both types of Coke. Well, how many populations? You got 2 samples, right? And each of those samples come from a different population. One's from regular Coke, one's from Diet Coke. And we're looking to see if they have the average weight is the same for both types of Coke. So, average weight is the same for both types of Cokes. So what parameter are we testing then? The mean. Good question. Is it going to be matched pairs or independent? Do you think the weight of a can of Diet Coke is going to have any relation to a randomly picked can of regular Coke? I know they're the same brand, but they're different cans, probably different production lines. So I'd say they're going to be different. Average weight is the same. So mu sub Coke equals mu sub, or maybe I should put regular, R, and mu sub diet. What's this going to be part of? HO. Mu sub regular equals mu sub diet, and then mu sub regular is not equal to mu sub diet. And of course, this is test E because we have independent samples, 2 populations. We okay with problem number 3 here? Problem number 4. Before you even read this, what does it look like before you even read it? We got president and main opponent. It's looking a lot like match pairs. And if you actually read through it, you would find that they're match pairs. You could do test a claim that presidents are taller than their opponents. So that'd be mu of P is greater than mu sub O. Mu sub P is less than or equal to mu sub O. Great. Data set 23, Old Faithful has data on a prediction error for the next eruption. Use a 1% significance level to test a claim that the population of prediction errors has a mean equal to 0. Well, at least you kind of know what parameter you're testing, right? Should have something that has a mean in it, mu. That's fine. How many populations are we dealing with? 1 or 2? 1. You're only drawing one sample from one population. So that'd be mu equals 0. And if mu equals 0 goes into our null hypothesis, then mu is not equal to 0 goes into the alternative hypothesis. That would be one population mean. So A. And so on. All right, there's one more like that one. It's actually one that we did in class. Now, as far as the questions that I could ask, I'll ask some like we just practiced, but some of them will actually ask you to do out pretty much all of the work here. So you have to state HO and HA. I give you the p-value so that it eliminates step 3. Step 5, reject H0 or fail to reject H0. And then step 6 is to do what? State your conclusion in words. So a couple like that. I asked you to interpret a confidence interval. We did practice something like that earlier today. You can be 95% confident that the mean difference in IQ scores is between negative 1.7 and 13.6. Okay. What value, what special value is in that confidence interval? 0. Good. So if you're doing this in association with a hypothesis test, would you be rejecting H0? No. Because typically H0 is going to include the possibility of equality, meaning the difference would be 0. So you probably wouldn't be rejecting H0. Go ahead. No, this one I'm just asking you to interpret the confidence interval. Yeah, but I'm also giving you a little heads up because I could give you a hypothesis test like this that instead of a p-value in step 4, I give you a confidence interval. So in problem number 10, you're going to have something with respect to 2 population proportions. Let's see. Not sure how to summarize these population proportions. I'm just going to, for expediency, call it P1 and P2. P1 and P2. Let's see. Test a claim that the smaller proportion of Chinese women spend some or all the money when compared to Chinese women given the same amount in smaller bills. So it's going to be a greater than in one direction or another. But the claim that you're going to be testing is going to be based on this confidence interval, the difference of these two proportions. Again, go back to kind of our previous problem, number 8. What number is not part of this interval? What special number? 0. If 0 is not part of this interval, then any claim that involves equality, like this one, can't be true. Piece of 1 minus piece of 2 would have to be less than or equal to 0 there. But if it equals 0, we can't reject this. Since this confidence interval doesn't contain the possibility of 0, you would reject H0. That would be your conclusion here, and then you can finish it up by stating your conclusion in words. So those are the kinds of problems to expect on the exam. Any questions on that part? Yes? What assumption is critical in testing a hypothesis regarding one population standard deviation? Oh, yeah, when we went over this back in section 8.4, I think it was. Let me just take a look here. Yeah, there was definitely one assumption that was critical in this, and that I think that comes out in the requirements here. Population has a normal distribution, and it says this is a fairly strict requirement. So that's something that you have to be careful about when you're testing a claim about one population standard deviation or variance. It's going to be the same when we actually even more. This is actually going to be worse when we start testing two population variances. You're going to have both populations come from a normal distribution, and that's a fairly strict requirement. If it's not true, then you shouldn't be using the hypothesis test we're going to conduct in 8.4 or 9.4. So, yeah, but how do you test whether or not something has a normal distribution? What have we looked at? Yeah, histogram, normal quantile plot, the most one outlier, and the Ryan-Joyner or Kolmogorov-Smirnov tests. So, all those are different ways you could look to see that. All right, that should be it. I'll be around in my office here and there, so if you have some questions, get a hold of me. Otherwise,